Hi. Um, Good afternoon, students. So today, in this video, um, like we want to talk about greatest elements, maximal elements, and then just to solidify things. Of course, one way to define greatest elements and maximal elements is to take the definitions for least and minimal and switch all the less than or equal to's for greater than or equal to's. Okay, but let's be, let's be a little bit more careful. Right? So, we have, let's see, let less than or equal to be a partial order. On A, and let's suppose we have a subset B. Okay, then A and B is the greatest element of B. If A greater than or equal to X for all X. Okay, that's the greatest. I guess we should say the greatest element of B. Okay. And that's what the greatest element is. And a maximal element, okay. Okay. I guess we'll just say also B and B is called maximal. A maximal element of B if basically there's nothing bigger than it. Not the same as being the greatest, as you can imagine, but if for all, I guess I should stick with A. Okay, A is the maximal element for all, let's say X and B, such that A is less than or equal to X, we have that X equals A, right? So that's telling us that anything that might be bigger than or equal to A is actually just A. Right, and so that's a maximal element. And we have the same proposition as we did for minimal elements. Well, because you can just take the proof and the statements and just switch all the less than or equal to's for greater than or equal to's. But okay, so we have let's take a partial order. And let's take a subset. Okay. Okay, B has at most one greatest element. Maybe there's no greatest element, but if there is one, it's just unique. Okay, 2. The greatest element is also maximal. If B has the greatest element B, then B is maximal. Okay, and then if B is a chain, then any maximal element is the greatest element. Okay. Of course, you can have a chain without any maximal elements. You could have a subset B which has a bunch of maximal elements or no maximal elements. You know, lots of different things can happen. Okay. So, oh, sorry about that. Okay, so before I end this video, let me just let's just try and like do a simple example. Or let's just talk about a few examples. Okay. Of course, let's take B to be a subset of the rational numbers with usual less than or equal to, and B is just going to be 1, a half, a third, a quarter, and on and on. Okay. Then B is a chain. Actually, Q is totally ordered, so any subset is also totally ordered. Okay, or linearly ordered is another word for it. Okay. So if it has a greatest element, if it has a least element, or sorry, that means that if it has a maximal element or a minimal element, they are also the least or the greatest, respectively. Okay. The greatest element is 1, and there is no least element. Okay. And so the 1 is also a maximal element. Okay. And since there is no least element, because B is a chain, a least element would also be, a minimal element would also be a least element. So since there is no least element, there is no minimal element. Right? Well, why? Well, whatever element of B you pick, say 1 over 10,000, I just choose like 1 over 10,001 is a smaller element than that. So there is no, so whatever you choose, I can always choose something smaller, meaning there's no minimal element, right? Okay, as another example, that's another example. Well, let's just make up our own partial order. I don't know, something like this. Okay. So in this example, let's label these A, B, C, D, D, E, F. And what is this diagram? What am I trying to describe with this diagram? Well, so here's my set A is going to be A, B, C, D, E, F. And I want to have like these relationships between all the different things. So I want to have A less than or equal to B, A less than or equal to C, B less than or equal to D, B less than or equal to E, C less than or equal to E, and C less than or equal to F. And also I want less than or equal to be transitive, reflexive, and antisymmetric. Meaning that because A is less than or equal to B and B is less than or equal to E, I want A less than or equal to E. Okay. But that is kind of captured by this diagram because I can follow a path of arrows from A to E. Okay. So I want to have these relations and also have less than or equal to be transitive, reflexive, and antisymmetric. Okay, so this actually defines what less than or equal to should be. Okay, so now let's think about what should be the greatest, maximal, least, etc. So you can see that in fact A is less than or equal to everything. Okay, so 1 is the least element. Okay. Right, for example, why is A less than or equal to D? Well, because B is less than or equal to D and A is less than or equal to B, so by transitivity. Okay. So you can see A is also the minimal element. And okay. Now what about so in fact you can see there's no greatest element. Okay. And 3, the maximal elements are D, E, F. Right? Because maximal means there's nothing bigger than you. If we look on this diagram, there's no arrows pointing up from D, E, or F. Okay. Okay. And you could imagine like more complicated things, you know, like we could combine these two examples and we could just make like kind of we could choose one of these and just make an infinite sequence of arrows going up and up forever. For example. And then we just have 2 maximal elements. And then kind of like this chain that goes on and on forever. Okay, and that's fine. And of course, many examples of partial orders, you can't draw them, but at least these kind of drawings can give you a simple idea of what some of the different things that could happen. Okay, so that is going to be it for this video. I'll make one more video on this topic about upper bounds and least upper bounds. Of course, that means we also need to talk about lower bounds and greatest lower bounds. Okay, so see you then.